Good afternoon and welcome to the CERIAS Security Seminar from Purdue University. Our speaker today is PhD student Wonjun Lee. His work is with Professor Elisa Bertino, and his topic today is detection and protection from denial of service attacks in grids by accountability agents. Wonjun?
Hi, good afternoon. My name is Wonjun Lee. I am working mainly with Professor Elisa Bertino. Today I'll be presenting about my research topics, detection and protection from denial of service attacks in grid environments by accountability agents. Before going inside, we need to specify three keywords. They are grid and accountability and denial of service. Three keywords mostly you might hear before. What is grid computing system? What is grid? Grid is the independent multiple clusters, something like resource nodes. So we call as a grid. There are many types of grid. So like a computational grid and data grid, and application grid, visualization grid, cloud computing, many things are existing right now. Computational grid is mainly focusing on computational operations, while data grid is mainly focusing on managing and controlling the sharing the distributed data. Here is an example. Like a Pete, who is a participant of the Open Science Grid, we call the virtual organization, which links shared resources, perform multidisciplinary simulations like a NW Fluid Linux, which is like a computational fluid mechanics applications. He wants to run this program, but he doesn't need to copy all the input data from multiple sites to the local machines, or he doesn't need to install the application in local machines. He can only learn program A in A state universities, like here, and the program B at B state university by reading data from C state university. What is accountability? Accountability is defined as A is accountable to B when A is obliged to inform B about A's past or future actions. If there is something wrong, A's actions should be traced back to the real entities and sometimes suffer punishment. Accountability is an important aspect of computer systems for assuring that every actions executed in the system can be traced back to some entities. Even accountability is very crucial for ensuring safety and security for a grid computing system. Because of the dynamic and multi-organizational nature of the grid system, which requires effective, efficient accountability system. But up to now, there is no comprehensive accountability system is designed. What is denial of service? This is an attempt to make a computer resource unavailable to legitimate users and target victims, in our case, located servers located inside or outside a grid. So in this talk, we will introduce the concept of accountability agent, job graph, cover record, log sharing mechanisms, and accountability data collection strategies in two strategies. And we show types of distributed denial of service attack that could exploit the grid resource. Finally, we will show some experimental results about the performance of the system. This is the overall architecture of the accountable grid system. Um, the one or more clusters belong to one resource providers. We call RP. And the one or two RPs belongs to one service providers. And there are a couple of service providers here. And the users can access grid resource by contacting service providers or directly to resource providers. The entry point where the first access is performed we authorize the users based on some users attributes or by some access control mechanisms. Accountability agents. The original role of the accountability agent is to collect accountability data useful for accountability and to map users' activity and resource consumptions to real identities. Accountability agents is able to trace back to identity providers. If the identity management system, which such as Shibboleth, is employed in the accountability system that authenticated the users. Accountability agents are located at multiple places across a grid node based on the criteria to satisfy two strategies. And shares accountability data to maintain co-relationships. And they have also each own database at the locations. So to hold individual users accountable, we need accountability data. Accountability data are collected in two strategies. First strategies is we call job flow-based strategies. If you summon your job into the sea of the grid, the job traverses to somewhere, node to node. The entry node is different from the execution node. And as you might run any parallel jobs before, the one job is divided into too many jobs to be run in parallelizations. So which means job is divided into many sub-jobs and traverses along the nodes across different administrative domains. So the activity of each job is studied as a function of job's traversal in an initial point. And in these strategies, a viewpoint moves along with the job and reports to accountability agents. It is something like if you see the particle of the fluid, the fluid moves or traverses from location to locations. So it is something like you are going with the fluid. Wherever the fluid goes, you're going to go. That is the strategies. And in these strategies, agent tracks down job's whole life cycle from creation of the process to the termination of the process. The second strategy is we call the grid node-based strategies. In these strategies, agent is only interested in a given locations at a given spatial of time. In this case, the viewpoint is fixed. The grid is composed of many layers, like the fabric layers, connectivity, resource, and the collective, and applications. Something like OSI 7 layers, starting from the physical layer, data link, networks, or something like that. So if you focus, if your viewpoint is fixed in fabric layers, which deal with resources like computational CPU cycles and the resource memory consumptions and the network bandwidth, you only collect data related to resources here. If your focus is in a connectivity layer, which involves communication and authentication protocols, your interesting data will be authorization decisions with the accepted user attribute. But taking individual strategy is not enough. By combining two strategies, we can get a more congruent, more comprehensive data, because two strategies are complementary to each other. The first two tables are collected from the job flow-based strategies, and this third one is from the grid node-based strategies. A job is submitted to service providers, and the job is divided into two jobs, the -2 and -3. Each assigned to compute node 2 and compute node 5. Compute node, the PBS 3839-3 is assigned at cn5.rcac.purdue.edu. At the third tables, if the agents detect some anomalies, like memory usage is abnormally greater than the other normal cases, it goes back to data collected from the job flow-based approaches. And then finally, we can, by combining these tables, we can know PBS 3839-2, which is assigned to CN2, may potentially cause bad operations. And then we take responsive actions. Log sharing mechanisms. Because accountability only belongs to a node, so it doesn't care jobs located at other nodes. So that's why we need to share the information between agents to get a whole information. Through the two concepts, job graph and the cover records, accountability system is realized in distributed fashions. Taking full advantages from a grid system is to run a job and divide to be run in multiple locations. So, as I mentioned before, job is divided into many sub-jobs, and sometimes jobs are merged and divided and looping for many times. So, extracting only one job to monitor is required here. So, directed graph is a suitable data structure to represent the flow in the interconnected complex system like a grid. This is the example of a job graph. The node, the vertices denote the green node, like service providers or the resource provider, head node or compute node, whatever. And then these edges denote jobs assignment. In this case, job 1 is divided into job 1A, job 1-B, and then job 1B is also divided into job 1B-1 and job 2. Here is the cover record for graphs. In this case, the agent, in terms of SP1, like here, the agent only cares about job 1 and write down all the record related to job 1, which is divided into job 1A and job 1B, with the handle information job ID and the timestamp when the job status becomes queued. For the case of RP1, they don't, it doesn't care any other jobs. It only cares about direct successor job and then predecessor job. So in this case, job 1 dash A comes from job 1 and SP1 or something like that. Next, in the case of RP2, agent only takes care about job 1 dash B. Okay, vulnerabilities in grid. There are many, as I mentioned before, there are many layers in a grid computing system. So that makes many vulnerabilities. They makes create many vulnerabilities in the grid computing system. For example, if we consider only about middlewares for grid and parallel computings, as you might hear about the middlewares for grid computing, the global toolkit is very de facto standard for the middlewares in grid computing system, which is web service containers. They have grid FTP applications. By using this, authorized users of the grid FTP server can access to the group permission of the root users. For the case of GSI proxy generation tool, GSI means Global Security Infrastructure. Proxy credentials data can be written to the file that the attackers can read. As another job schedulers, SunGrid engine gives threats of buffer overflow. They may be exploited by unbiased local users to gain elevated privileges. Besides these vulnerabilities, in low levels, some researchers have found that collisions in MD5 signatures algorithms. They published the vulnerabilities of the MD5 in recent Crypto 2009 conference. So if you exploit those facts, you can make rogue certificate authorities. By using that schemes, you can attack one point located in many layers of the grid computing system. Grid computings delegate to each other. So if you attack one point, most of the resources cannot be protected because of that. I'm gonna introduce two attacks in grid computing system. It's not like the other general distributed denial of service. In this case, the victim is located inside a grid. Examples of the victims would be gatekeepers or schedulers. The schedulers, which is located at head node of the head node is the contains the schedulers in one or more clusters. Like if the schedulers is out of service, every compute node connected to the schedulers is not being used. Or the one of gatekeepers is out of service. The job submitted to gatekeepers cannot go to further, cannot go to other gatekeepers or cannot go to other head node or whatever. So if a huge number of jobs are submitted to a queue, the queue cannot properly process all the jobs. For example, if you were using any job schedulers like a portable batch system we call PBS web services or PBS schedulers or Condor, there is the queue there. Have you heard about any Condor and PBS before? Okay. So if you want to use, if you want submit your job, you're gonna submit your job to one of gatekeepers, and that job is come to the service providers or resource providers. Their job schedules, we call the PBS or Condor, is connected to the Globus containers, and then the job goes into the queue to be scheduled. If you, as attackers, if you submit huge amount of jobs at a time for a short time, the queue is broken and the queue is gonna be out of service. It's in reality, the queue is very weak. So if you around over 1,000 jobs at a time to the current queue, Condor queue, that is serviced by Purdue University, the cluster is gonna be work. It's not gonna work. So the queue itself is very weak. So in this scenario, to increase the queuing, the attacker adds jobs in the queue faster than the time required for the jobs to execute the job, to execute the queue. Like if you submit huge amount of jobs at the speed faster than job executions, probably the remaining job will be increased, right? So until all the attackers queue the jobs complete and exit, no more jobs cannot be further proceeding. This is another type of attack that exploits the grid resources, targeting the server located outside the grid. In this case, victim will be a very important site like high-profile web servers such as banks, credit payment gateway, or mission-critical government hosts. So, for the general distributed denial of service, we don't have any control on the remote side, right? So that's why, but the accountability agent has authorization to collect data from all of the layers in grid system. So in this case, we need approach in different ways, detecting not in destinations, but in source levels. In this case, attackers generate network traffic toward the victim node. And the outbounding network traffic can saturate the entire network bandwidth in a short time. The compute node does not know, but the compute node does not know which application is running. Right? So to cover those two attacks, accountability has additional functions like detecting anomalies and then issuing alarms and then taking responsive actions. The first, detecting anomalies. Accountability agents use existing anomaly detection mechanisms like a statistical model or entropy-based approaches, etc., for monitoring resource consumptions. If there is no tool for specific resource consumption monitoring, it uses directly other ways, like by gathering resource consumption data from log informations generated by applications, or by using a system command like lsof or strace, etc. And then if an anomaly is detected, agent issues alarms based on the severity of the threat and the likelihood that the anomalies is in fact attack. Raising alarms. This one is to notify the possibility of an attack. Agents coordinate with each other by means of alarms. In this case, an alarm contains not only the warning itself, but also crucial job information like handler information, job ID, and alarm issuers' identities, and destination information about possible attacks. This alarm is classified as light, moderate, and critical based on the severity of the threat. And the last step is taking responsive actions. Intuitively, if you detect some anomalies, the first thing that you need to do is the killing process, running on behalf of the malicious jobs. And then also killing the pending jobs to block other sub-jobs that can potentially harm other nodes of the job graph. And then finally, you will identify attack patterns for future preventions by recording the patterns and analyzing later. This is the visualization of the three steps. If the anomalies is detected at compute nodes, like here, this blue nodes denotes the compute nodes, and then agents located at compute nodes raises write alarm to predecessor nodes. In this case, predecessor nodes will be a resource provider or a head node. Based on the calculation of how many jobs are divided into the from the same node, the agent in head node raises another alarm, which is a moderate alarm. Based on the all analyzation and finally entry node, which is a root node of the graph node, makes decision by sending critical alarms. Upon list of critical alarms, the agent in each compute node take responsive actions like kills processes like that, and then disconnect ongoing attacks. Okay, so we go on to the how to detect at the victim node and source node. The first, detection at the victim node. In this case, there are many resources, but in this case, we only consider the one of queues that I mentioned before. From the data obtained in green node-based strategy, the agent detects anomalies concerning resource consumptions by using well-developed methodologies like statistical modeling and entropy-based approaches. However, such approaches are often not accurate because in complicated grid systems, they may causes high rate of false detectiveness, false positiveness. So, in this, even if agents detect anomalies from the grid node-based strategies, it doesn't immediately consider that incident as an attack. Rather, it uses data collected by job flow-based strategies, which collects about the job data, where many contributor data is there. So, okay. Here is the to detect anomalies concerning resource consumptions, we need to employ the concept of sliding time windows. Sliding time windows means how often you're gonna monitor the resource consumptions. For the case of queues, like as I mentioned, there are many factors to decide sliding time windows. The first one is average number of jobs entering the queue per time unit. And the next factor is the average processing time per job. So if you the difference between incoming and outgoing job flows, what will you get from there? You will get the rate of remaining jobs, right? Because if you think about the fluid, like flowing into the hose, if you put more fluid, and then the outgoing fluid is not that fast, then what happened? What will happen? The fluid will remain in the hose, right? So it's something like that. If the job incomes the queue very fast, but the execution time is very slow, the size, the queued job, the number of queued jobs will be increasing. So by dividing available maximum size of the queue by the rate of remaining jobs, you will get time windows, which is the time required to fill up the whole queue. So if the size of the W gets small, you need to monitor very often. But it implies that the cost of the resource consumptions will be very high. Detections at the victim node. Okay. There are two tables here. The left one, the left table is from the job flow-based strategies. The right one is from the grid node-based approaches, monitoring the resource consumptions. Right? If for every in attribute at the right table, the number of queued jobs are specified at the parentheses there. So if the sliding time window comes to 10:38, the agent looks back 10 seconds. If we assume the time slide, the window time window is 10 seconds, for example. It looks back for 10 seconds. In this case, from 10:3:18 to 10:3:09, only five jobs are queued here. So if we assume also a threshold to define anomalies as a 20, for example, in this case, this resource consumption looks very normal. Right? If the time slide comes to 10:3:28, you're gonna look back 10 seconds from there. This case from 10:3:19 to 10:3:29, from 10:3:19 to 10:3:29, altogether 24 jobs are queued in a certain queue. So because threshold is 20, we can say that it looks very abnormal. But in this case, but the agent does not immediately trigger defensive actions against those, but simply raises a light alarm to the direct predecessor node. From the left table, which maps handler and job informations here, the handler is very unique for all jobs, for all graph. So if two subjobs have the same handler, they came from one job and divided. So from the left tables, from job 6, which is queued at 10.3.19, from job 6 through job 27, when we check how many handlers are there, we can know that 20 out of 24 submitted jobs have the same handlers, which means 20 jobs are from the same job, divided from the one job, which means very weird, which means very abnormal. Because if you think about the grid, characteristic of the grid, where a job is divided into many jobs to be run in multiple nodes in parallelizations, or multiple sub-jobs resubmitted to our schedules again, it's not happen. It doesn't happen very often. Even if some divided jobs gonna assign to or resubmitted to the schedulers, the percentage of the same job is not that high, like 80%. Detection at the source node. So this is different. The target node is outside of the grid, so we don't have any control of the victim server. If we use many hundreds of thousands of computing nodes, and then you're gonna put some malicious code, like a very simple, if you put, have you ever heard about the AB, requesting pages to check how many loads can be requested to a certain web servers. Like a long time ago in South Korea, the incidents happened by the attackers. The major web portals are down by using this type of attacks. The attackers that time used the AB, I heard, requesting so many pages request at a time. So because there is limited capabilities of the web servers, if many requests comes at a time, sometimes the web servers becomes very slow. You might experience the Facebook. Sometimes Facebook, if you access, sometimes it's very slow, right? So thus the approach, detect at the attacking nodes is required. So based on the observations, first one is normal behavior of compute nodes is to execute jobs at computational resources in the grid. So when the destinations of most of the network transactions have the same address, this job can be considered very suspicious. Detection at the source nodes continued. When the agent in compute nodes detects packets are sent outside a grid as an execution of the job, it combines job information to raise a light alarm to the direct predecessor agent. The agent in header node determines from the reported alarms how many subjobs have the same destinations for their network transactions. If the number of subjobs is very high, we can consider ongoing attack is suspected. and the response action is taken from there. Without an intentional purpose, it is unlikely to experience the same destinations for a number of packets within a short time. Based on two approaches, we did some experiment like here. This is a real architectures of grid. And we put a grid accountability agent here, and we located our agent at three important strategical locations. First one is entry point, where the job is first submitted to. There we can get access control informations, or the decision of information about decision about authorizations. And then we locate our agent in scheduler levels to get scheduling informations. And then finally we put agents in real compute nodes to get our resource consumption usages. One job is submitted too many first submitted to service provider, and then it comes to one of head node, and then divided into 40 into 30, 35 compute node here. And then this job execute job assigned at compute node execute to generate huge amount of a packet to the head node here, or request overloads page request to shut down this to shut down the head node here. This experiment is done in emulate testbed, where the real physical machine, virtualized physical machines are provided there. And then we used Global's Toolkit as a web service, grid web service containers. And then we used PBS, portable batch schedulers, as our schedulers, and the PostgreSQL SQL as a database management system. We use two head node and two RPs here. Okay, here is the experiment and the evaluations. This experiment is to show the wait time of the normal jobs until the jobs goes to active state, which is running state. In grid computing system, the job when the job scheduled goes to the queue, it becomes a pending state, and then it becomes active state, and running and done. There are 4 big states, which means this is the wait time of the normal jobs to exit the queue. The first and this x-axis means the normal job is submitted to the queue when the malicious job, attacker's job, fears queue 30%. We only use we assume that the size of the queue is 35. So, which means when the queue is filled at 30%, 60%, 90%, and 100%. So the first line denotes the wait time of the normal job when the time window is too large, or our system is not there. In this case, the wait time increases based on the portion of the filling of the queue. So in this case, the job is, we assume maximum Q is 35 since it is not feasible in our test bed. We also check that 19 jobs are queued for every 100 seconds, and the 78 seconds takes to exit the job. And we use the two compute nodes to run the real applications. In this case, from the equations, we get 210 seconds is the optimal time window. So we checked time windows less than 210 and greater than 210. For the case of 1.5 times from the time window, or 2 times, which is 420 seconds, these two lines, we can know that the time takes much more time, very, very long, because the malicious job is detected, is eliminated after the large time windows is passed. Because the time window is very large, at the next step, the malicious jobs are eliminated. That's why those two jobs takes too long here. But the time window less than 210 seconds, that doesn't have a big difference, because the queued jobs is very small, so threshold, it didn't satisfy the threshold. If we assume the threshold is around 70%, until it doesn't know until the 70% of the job is filled in the queue. So that's why we came to know that 210 seconds is very optimal here. But in this case, upper lines, since attacker's jobs are queued before the normal jobs and run for a long time, the wait time increases here as the number of attackers' queued job increases. In contrast to our baseline case, the time windows are all decreasing here because the normal jobs submitted close to the end of sliding time window do not wait until detection is made at the next sliding windows. The next experiment is about recovery time for different test case for attack durations. In our case, I did experiment like I made the real servers running on Tomcat servers in different outside of a grid. And then I used 35 MLab testbed, and I generated a huge amount of page request to these servers. And then finally I found that this server becomes very slow. And then when I just clicking this server from the outside of from third servers, it doesn't respond to legal users. So in this case, attack durations is from 120 seconds to 400 seconds, which means loading pages for 400 seconds continuously and concurrently. But even though the attack duration is different, the attackers the time for recovery doesn't depend on the attack durations. In this case, attacker's job assigned at multiple compute nodes send multiple requests to the target web server simultaneously. Um, in our experiment shows that the recovery time is actually not related to the duration of the attack. Therefore, even for long-lasting attacks, our system can detect attack and take a responsive action within 1 or 2 minutes. Okay, conclusions. We presented a distributed approach for end-to-end accountability in grid systems. Also, we introduced the concept of accountability agents performing a wide range of information, gathering and keeping track of submitted jobs and users. We also discussed about different kinds of denial of service attacks that could exploit grids and proposed detection and protection mechanisms based on accountability agents. Also, from the experiment, we showed the accountability enabled grid computing system effectively detects and protects the current denial of service attacks. Okay, any questions? Yes.
You said that in your test bed, 210 seconds was the optimal time. Would that be the same in a larger grid or grids with different capabilities, or do you have like an algorithm to determine the optimal time? Or
Yeah, actually, this one comes from these equations. Right. So, because the Amina test bed doesn't allow to shut down the rear queue from the PBS server. So we only assume that the maximum size of the queue is 35. We assume that if the 35 jobs are queued in a certain queue, in a PBS queue, we consider that it is filled, it's fully filled. So from the measurements of the rate of incoming jobs and the rate of execution, so we calculated 210 seconds from these equations. It'll be different from in case of other situations. But yeah, these equations is just a recommendation for in terms of administrators, by estimating the rate of incoming jobs by attackers, and then measuring the execution times. And then, because we know the number of the compute nodes, and we know the number of the maximum size of a queue, we can calculate the possible time window from these equations. Do you have any other question? Okay. Okay, thank you.